Hello and welcome to Pathfinder Analytics. In this video, I'm building a complete end-to-end data platform from raw API ingestion to a deployed Databricks application for visualization, all the way to an AI-powered self-service analytics experience with AI-ready Genie spaces. The best part about the project is that it's going to be on the Databricks free edition, so it won't cost you anything. Here's what we're covering. First, we'll implement a full medallion architecture pipeline, pulling real-time earthquake data from the USGS API. Second, we're going to deploy a live Databricks application, a Streamlit dashboard with a 3D interactive globe showing earthquake activity which is filterable by significance and time range. And finally, we're making the whole platform AI-ready with an AI-ready Genie space. This means that end users can ask natural language questions on the data and get instant answers without writing any SQL. By the end of the project, you'll see how to take raw external data and turn it into a fully deployed, AI-enabled analytics product all on Databricks. Okay, so let's get into the details. To start with, let's talk about the prerequisite skills. I classify this project as intermediate to advanced level. It's aimed at people who've done a few projects on Databricks and want to level up. You should be comfortable with the Databricks platform, have a decent grasp of Python, SQL, and PySpark, and understand Delta Lake fundamentals like merge operations. Some experience with Databricks asset bundles is also helpful. You should also be comfortable working in an IDE and with basic Git operations. Knowledge of Streamlit is a plus, but it's not essential, as it's quite easy to pick up. With the prerequisites out of the way, let me get into the solution architecture. To start with, let's look at the ingestion and transformation. We're building a lakehouse that stores earthquake events data. The data can be ingested via API calls, and it returns the data in JSON format. We'll use the Python requests library to ingest the data as JSON and then convert it into a Spark data frame. Since requests is a Python library, if we want to parallelize this across the Databricks cluster, we need to use the PySpark custom data source API, which is what we'll do for this project. We'll use PySpark to process the data from bronze to silver to gold. The bronze layer will store the data in its original, highly nested format. The silver layer will cleanse, validate, and enrich raw earthquake data using checkpoints to track the last processed source version. The gold layer will create analytics-ready, aggregated tables for the Streamlit dashboard and the AI-ready Genie space. Once we've set up our lakehouse, we'll create a Streamlit application that provides an interactive 3D map visualization of earthquake events, with filtering capabilities and summary statistics. Using the gold tables, we'll also create an AI-ready Genie space so that business users can query and ask questions on the data in natural language. In terms of key features of the project, I've mentioned that we're using the PySpark custom data source API to build a custom Spark connector to ensure we're leveraging the benefits of distributed processing. We'll also use change data feeds and checkpoint tables for downstream incremental processing, and we'll ensure idempotent writes by merging on a unique key. Local development and deployment will be done via Databricks asset bundles. The overall solution will demonstrate an end-to-end AI-powered analytics platform. In terms of setup, please ensure you have the Databricks free edition account. I'll provide a link to the registration in case you don't have this. In your local machine, you should have Python version 3.11 or above, pip or UV as your package manager, and the Databricks CLI. I'll be using version 0.285. I'll share links in the video description for all of the download instructions and any other details. In case I forget anything, please refer to the readme.md markdown file in the GitHub repository for this project, which I'll also share in the video description. For this tutorial, I'm going to do things a little bit differently. Usually I'd build the logic bit by bit, and at the end run the pipelines and deploy the apps. But this time, I'll start with the show and tell. We'll deploy the project, run the pipelines to populate our lakehouse tables, launch the Streamlit application, and set up the Genie space, so you can see the end result first. I'll then give an overview of the code and the logic that I implemented, starting with the pipelines and then the Streamlit application. So let's jump in and deploy the project. To access the code base for this project, please use the GitHub repository via this URL, which I've provided in the video description. Copy the HTTPS path. I'm working locally on Visual Studio Code. You can use the same or whatever your preferred IDE is. On your IDE, open up the terminal. That's Z shell on a Mac or Git bash on a Windows. Navigate to your target directory on your local machine. So for me, that will be desktop. So I'll cd into desktop and then type git clone, followed by the HTTPS path of the GitHub repository. And then it will clone it into that target location. So if I type ls, you can see here is the Earthquake Analytics repository. Once that's done, open up the project in your IDE. So click on Open Folder, and then here is Earthquake Analytics. Okay, great. Let me walk you through the project structure at a high level. We'll dive deeper into the actual code later. Starting at the root, we have this databricks.yaml file. This is our Databricks Asset Bundle configuration. Let me walk you through the key sections. At the top, we have the bundle name, which is Earthquake Analytics. The include key indicates that there are configurations from other files that need to be taken into account. Specifically, this resources folder here. So this contains additional configurations, which extends this databricks.yaml file. The artifacts key packages this utils folder into a wheel file. This means that we can import functions from our utils module. The wheel gets deployed and created automatically every time we deploy the package. We then have the resources section. This references our job and app definitions. The job definition is here in this resources folder. As I said, this extends this configuration file. Importantly, this is the configuration for our Streamlit application. This specifies where the source code is, which is in this Streamlit App folder. We've also specified some variables, as you can see here. We have catalog and schema. Below that, we have targets. This is where we define our deployment environments. We have dev and we have prod. Each target can have different settings, like a default catalog and schema. So as you can see, we are providing the variables catalog and schema here. So the default catalog name is QuakeLake and the schema is USGS Earthquakes Dev. Next, we have the pyproject.toml file. This is important for our utils module. It defines our Python package metadata, the dependencies we need, and crucially, it tells Python how to build our code into a distributable wheel file. When we run UV build locally, or when Databricks job runs it, so as you can see, we have UV build wheel, then it reads this file to know how to package everything up. By default, it looks for a directory that matches the name here, utils. So here's the directory. It then packages everything up in this directory into a wheel file. So now let's go to this utils folder. This utils folder contains our shared Python code. This is what gets built into the wheel file I mentioned earlier. So let's start by looking at this helpers.py file. This contains functions organized into 5 categories. You have catalog and schema management, date range helpers, write operations, data quality helpers, and change data feed helpers. We also have datasource.py. This contains our custom PySpark data source for the USGS API. This is how we pull earthquake data in a distributed way. In this resources folder, we contain our job definition YAML file. So let me explain the key parts. The job has a name, which is called Earthquake Analytics ETL job. We're defining a trigger, so this tells the job how frequently to run. We have some parameters. These are job level parameters, and they get injected into tasks, and we've defined the tasks here. Each task specifies which notebook to run, and they're chained together using this depends on key. So this task depends on the previous task, and so on. Before any of our notebooks run, we have this Python build wheel task here. This task installs the wheel on our cluster so that we can import any of the functions from this utils package into our notebooks using standard Python imports. This keeps our notebook code clean and our shared logic reusable. We then also define the environment key here, and then below we have the environment configuration. We're using the default environment of 4, and then as you can see under dependencies, we have our wheel file, and this is the location that the wheel file gets built in its own dist folder. Now let me go over this ETL folder. This ETL folder contains our 3 pipeline notebooks following the medallion architecture. This bronze ingestion notebook pulls data from the USGS API into our bronze layer. This silver transformations notebook cleanses and enriches the data. And then this gold aggregation notebook creates our analytics-ready gold layer tables. We'll go through each of these in detail later. And then finally, we have this Streamlit App folder. It contains everything that we need for our Databricks app. We have this app.yaml file. This contains the app configuration. It defines metadata, like the app name and description, plus it contains environment variables. So we have a Databricks warehouse ID, which we can provide, a catalog name, which has the value of Quake Lake, and the schema, which is given the value of USGS earthquakes dev. This is the command to run when we deploy the app, streamlit run app.py. So it runs this file. This app.py file is the actual dashboard code. This contains our Streamlit application, which contains a 3D globe visualization, a filtering sidebar, metrics cards, and various charts. So when the app is deployed, Databricks runs this file using the command we specified in this app.yaml file. There are also README files in various locations. This is the README file at the project root. We also have README files under the Streamlit app folder, ETL folder, and so on. So this will provide additional information for you to refer to. So now let's deploy this project and see everything in action. To deploy the Databricks project, we can follow the steps outlined in this readme.md file at the root of the project. So I have it open here. Let me just preview it in Markdown, and then let me just expand this space. So for now, let me just minimize my terminal. So navigate down to the Getting Started section. Here we are, Getting Started. So we've already cloned the repository. Now let's install the dependencies. You can do that via UV or pip. I'll do it via UV. So when you're in your project folder, in your terminal, you can type UV sync --dev. This will install all of the dependencies in this dev group in the pyproject.toml file. So it'll install all of these dependencies. That's needed for this project. So let's run this. Okay, so that's worked. So let me clear the terminal. And then the next step is to configure the Databricks connection. So to do that, we can type Databricks configure, but I'm also going to provide an additional flag. So if I type Databricks configure, then we can configure a profile called dbx_free. So if I don't provide this profile flag, it will just configure a profile called default, but I just want to give it a custom name. So that's just an optional extra bit. So once you type enter, it will ask you for your Databricks workspace host. So navigate to your Databricks workspace. As I said, I'm using a free edition Databricks workspace. This is the host, so let me just copy it. Now let me paste it in, and then press enter. It will then ask you for a personal access token. Back in your Databricks workspace, go to Settings, Developer, Access Tokens, Generate New Token. So let me just call the token Earthquake Analytics Project. And then make sure you copy that. And then paste it in. Okay, so we can view all of our Databricks profiles by typing Databricks auth profiles. So you should have a profile with the same name you specified, dbx-free. If you didn't provide this flag, then it will just be called default. As you can see, it's valid. Okay, so now one thing we need to do is make sure you copy your Databricks workspace host, and then in your databricks.yaml file, under the targets key, we need to replace this workspace host with our Databricks URL. So I'll do it in prod as well, even though we're only going to deploy to dev, and save that. Now we need to set some environment variables for the Streamlit app. So in this Streamlit app folder, open up the app.yaml file. As you can see, we need to provide our Databricks warehouse ID. So navigate to your Databricks workspace. Under Compute, you should have a serverless SQL warehouse. So select the warehouse and then copy the ID. So this is the ID, copy that. And then you can paste that in the app.yaml file. And then save that. Okay, so now we're ready to deploy our project. To deploy the project, we can simply type Databricks bundle deploy, and then specify the target as dev, even though that is default, and then the profile flag for your Databricks profile authentication. I only have one, but if you had multiple, then you can explicitly say which profile you want to use. So I'll just specify dbx-free just to be explicit, and then run. So it should start deploying everything to your Databricks workspace. Okay, so the deployment is complete. In your Databricks workspace, under your workspace folder, under your user account, you should see a bundle file. This will contain the Earthquake Analytics project folder, and then within that, you should see dev, which is the target, and then here are the files. Under artifacts, you should have a wheel file. This is the utils wheel package. And then under files, you should have your project code, as you can see. Under jobs and pipelines, you should have a job that was deployed. It should be called Earthquake Analytics ETL job. If you click into it, just as per the configuration, it contains 4 jobs. It contains 4 tasks: a Python wheel task, bronze ingestion, silver transformation, and gold aggregation. Under compute, apps, you should also see a Streamlit application. So we've successfully deployed our project. Now let's run the job so that we can load data into the lakehouse. Click on your job and then click on Run Now. Every time we run the pipeline, the default setting is to ingest 1 full day's worth of data from 2 days ago. So for example, if today is Wednesday, then it will pull all of Monday's earthquake events. Let's click on Run Now and then wait. Great, so the job's finished. Let's check out the catalog. So we should have a catalog called Quake Lake. There's a schema called USGS earthquakes_dev. And then we've got all of our tables. This checkpoint table, so let me just preview the sample data by selecting the compute, stores the latest processed version of each table, so that in future runs, it only processes incremental changes. So as you can see, the latest processed version is 0 because the tables just got created. So this is the Delta history version. We also have the bronze events table. This contains the data in as close to the raw form as possible. It's still in highly nested format. So as you can see, we've got the properties, and then we've got the geometry information, which is the coordinates, and then we've got all of the keys. So these are just additional metadata columns that we've added. We then have this silver events table. This table has applied some transformations to the bronze table, and all of the nested attributes have been flattened. And the data in general has been enriched. We also have 3 gold layer tables. Gold events map, if I preview that sample data, contains individual events that are for our 3D map display. We then have the gold daily summary. This contains daily aggregations, and we currently only have processed data for 1 day. And then we have gold regional summary. This will contain regional aggregations, as you can see. We can query the data using the SQL editor as well. So let me just confirm what dates have been processed from the gold events map table. So if I open up a query tab, and I can paste in the following query. Select max event time, min event time from the gold events map table, and then I can run that. And as you can see, we've processed data for the 29th of January 2026. So for you, this date will be different depending on when you're currently watching this video. So for me, the current date is the 31st of January, so we've processed data for the full day, which is 2 days prior to today's date. Okay. So now that we have 1 day's worth of data, let me grab the data for the last 30 days or so. To do that, we can actually just go to our job, and then we can run with different settings. And then we have job level parameters. So I can modify the start date and the end date of the data that I want to pull. So let me just get the 1st of January 2026. So I will do it in this format. 4-digit year, 2-digit month, 2-digit day. And then for the end date, let's just say 2026-01-29. So even though there's some overlap, it doesn't matter because our pipelines are idempotent. So even if this date range overlaps, it won't duplicate the records. And now because we're processing data for 1 month, let me increase the number of partitions. Let me just say I would like 2 partitions. I'll explain how this num_partitions key works later on, but for now I've just set it to 2. And then click on Run. Okay, so the run has started. Let's wait for it to finish. Okay, that's finished. Now if I go back to the SQL editor and then rerun this query, we should have data from the 1st of January to the 29th of January. So that's just for me, but for you it will be for 29 days or so. So let me run this. And as you can see, the minimum event time for me is now the 1st of January 2026 up to the 29th of January 2026. So now that we have the data in the lakehouse, let's deploy the Streamlit application. So under Compute, go to App, and then you should see this Earthquake Analytics app. Open up the app and then click on Start. We then need to wait for the compute to start. Once the compute started up, click on Deploy. It will then ask you for your source code path. So for the source code path, you want to navigate to the bundle, and then under Files, you should see the Streamlit app folder. Select that, and then click on Deploy. So the app is now being deployed, and then this is the app URL which you can use to access the application. Before we actually launch this app, let's make sure we have the appropriate permissions. Under Authorization, there should be a service principal for app authorization. Click on the service principal name. And then under Catalog, make sure for the Quake Lake catalog, it has Use Catalog Permissions, and then paste in the name of the service principal. So here it is. And then click on Confirm. Navigate to this schema, USGS Earthquakes Dev. Again, give it the appropriate permission, which is Use Schema. Specify the principal, confirm, and then also for the gold tables, give it select permissions. So grant select on the gold table. So let me just quickly do that for all of the tables. Okay, great. So once you've done that, go back to Compute, Apps, and then you can open your app by clicking here, or you could just access it here, and then here's the app URL. So it will now open up the application. So this is our Quake Lake dashboard. It's a 3D interactive visualization of earthquake events. So let me walk you through what we're seeing. So if I just scroll back to the top here, we have some high-level metrics. Total events, the number of high significant events, the maximum significance recorded, and the number of tsunami warnings in that selected period. Below, we have the earthquake map, which is a 3D visualization. Each column, as you can see here, represents an earthquake event, and the height of the column corresponds to the significance score. So taller columns are more impactful earthquakes. The colors indicate severity. So as you can see, the red are the most significant events. So we have red for severe, orange for major events, yellow for moderate, and then green for minor earthquakes. We also have cyan as well for low significance. You can click out and rotate the globe as well. You can scroll in and zoom out as well. If you hover on any of the events, you can see all the key statistics. So let me just hover over this one. As you can see the location, the magnitude, the depth, the significance, and so on. Let me change the time range along this side panel filter to last week. And now this will update. As you can see, these are the earthquakes that happened in the last week. and then we can see all of these events have updated. Further below here, we have a daily event count, the top regions in terms of significance, and then we have a table here of high significant events. So that's our Streamlit dashboard. It's powered by the gold tables that we populated with our ETL pipeline. As I said, I'll run you through a deep dive of the code for the overall project shortly, but first, let's create an AI-BI Genie space. To do that, we can navigate to Genie. AI-BI Genie is one of the coolest features in Databricks. It's an AI agent that lets you query your data using natural language. Think of it as a natural language interface to your data. Instead of writing SQL queries, business users can just ask questions in plain English, and Genie will generate the SQL, run it against your tables, and return the results. To create a Genie space, just click on New, and then select your tables. So in this Quake Lake catalog, I will select all of the gold tables. So under the hood, it will use a large language model that understands your table schemas, column names, and relationships. When you create a Genie space, you connect it to these tables, and it learns the structure of your data. And that's why we built these gold layer tables. They're clean, well-named, and aggregated for analytics. This makes it much easier for Genie to understand and generate accurate queries. So let's create the Genie space. Let me give the space a name. I'll just call it Quake Space. Okay, great, so that's created. Under Configure, you can see the data that we've given it access to. These are our gold level tables. We can also specify detailed instructions. So we can provide plain text, free-form background information that Genie can reference. We can also specify various joins within the tables so that Genie knows how to relate the tables and write the correct SQL. We can also teach Genie by example in terms of giving it common SQL expressions that it could use. If you want Genie to use business logic correctly, then we can also define reusable functions here. I won't go into too much detail as I'll leave this blank, but I do encourage you to try and experiment with all of these instructions so that you can compare the outputs you receive. So now the Genie space is set up, we can ask some questions. Let me ask it a question. What was the earthquake with the highest significance? So it's located the relevant data, it's walking you through its reasoning, and then it gives you the response. So as you can see, here is the actual raw data. You can see the code that it used, and then here is the text response. So the earthquake with the highest significance was a value of 1017, which is what we saw in our dashboard. And here's the location. Business users can access the Genie space by going to Databricks 1. So to do that, you click here, and then you go to Databricks 1. And then here's the space, and it will open up the space. So this is how business users will interact with it. So let me ask another question. What region had the most earthquakes in the last 7 days? So it's already found the relevant data, and then it's given you the response. So the region was the geysers in California with 792 events. You can see here's the result table, and then here is the code that it used in the background. Genie spaces can be a really powerful way to allow end users to self-serve on your curated data. So hopefully you found that really interesting as an end-to-end project. We've got the data flowing from the USGS API through a full medallion architecture into a Streamlit application with a 3D visualization, and it's all deployed and running on a Databricks workspace. We also built a Genie space for end users to query the data in natural language. Think of what you just saw as the completed Lego set. But how did we actually get from 0 to that? What are all the pieces and how do they fit together? In the remainder of this video, I'll give an overview of each component: the custom data source, the ETL notebooks, the helper functions, the deployment configuration, and the Streamlit application. Just keep in mind that there are a lot of intricacies, and while I will give a sufficient overview, in order to really grasp what I've done, you should take time to review the code in detail and do your own research and self-study to fill in any gaps in your knowledge. The codebase contains lots of helpful README files and links and resources for your reference. I want to start off by taking you on a deep dive into how we're actually getting our earthquake data. Understanding this is crucial because the solution that we've built to ingest the data, which is the custom PySpark data source, is what makes our pipeline scalable. I've got a Scratch notebook. If you go to Bundle, your earthquake events, Dev, Files, in this Scratch folder, there should be a notebook called USGS API. So open that up. And let me just expand this so you can see everything clearly. The USGS, which stands for the United States Geological Survey, provides a free public API for earthquake data. This is the official documentation in case you want to take a look. I'll link it with this video. Let's explore how it works. Here's the API endpoint. We pass in parameters like the format, start time, and end time. The format is GeoJSON. This is a standard format for geographic data. If we run this line of code, it should fetch 1 week of data from the 1st of January 2000 to the 7th of January 2000. We do request.get by providing the endpoint URL and the parameters. We get a response object. We then use the JSON method to get the response in JSON format and store it in this data object. So let's run this. Okay, so we've got just over 1,000 earthquake events. The API is fast and it returns data quickly for small ranges. Let's check out the specific structure of the response. So let me just run this cell. So we have type, metadata, and features as top-level keys. If you scroll all the way to the bottom, there should be another key called bbox. That is for bounding box. If we run this cell, we can see the metadata key. So we've got this many records, which is just over 1,000, and the status was 200, which is successful. We can also drill into a feature. So let me just print one event. So this is one earthquake event. Every event has 4 main parts. We have the type, which is a feature, and then the properties. This is a dictionary containing all of the event metadata. So it can be like the magnitude, the time, so this is the epoch time. We have things like the status, it was reviewed, so this event has been reviewed, the significance, and other information as well. This geometry key are the coordinates. It's an array of 3 elements, longitude, latitude, and the depth. And then we have a unique identifier. We'll use this to ensure that we don't have duplicate records. So if I run this cell, we're converting the API response in JSON into a data frame object and displaying it. And notice the schema here. I've used the top level keys, type, properties, geometry, and ID. Properties in geometry are nested arrays storing key value pairs. So here's the data frame. So we've got feature, and then here are the properties, and then here's the geometry objects, and then there's the ID. So this should look very similar to our bronze level table. Okay, so that was all good and well, but the problem is when we want to return a large number of records over a longer time period. The problem is that the USGS API has a hard limit of 20,000 records per request. If your query was to return more than that, then the API will fail completely with a 400 error. I can show you by running this cell, where I'm trying to retrieve 1 year's worth of data. As you can see, the status code is 400. A single month of data is typically safe. It's usually under 20,000 events, but anything larger than that, then we'll need to partition our requests into smaller chunks. One way to do that is by breaking the date range into smaller chunks so that we stay under the limit. And this cell is doing exactly that. So let me zoom out a little bit so you can see a bit more of this. Let me walk you through what it's doing. It still downloads the 12 months of data, but instead of fetching it in a single massive request, it splits the date range into 25 smaller partitions. It then iterates over those partitions sequentially. It makes one API call per time slice, and then it collects the results into a list called all features. So let me go over each bit, because I appreciate that can be quite a lot. So first, I'm defining 2 simple date strings, the start date and the end date, so start S and end S. I then decide how many partitions I want to split that year into. I've chosen 25. This means that instead of making one API call for one huge chunk of data, I break the year into 25 smaller slices and fetch each slice separately. I then take those dates, which are strings, and I convert them into actual datetime objects in Python. I'm also attaching the UTC time zone to be extra specific. And then I'm calculating the total number of seconds between the start and the end dates. Once I have that, I divide the total seconds by the number of partitions so that I get the exact size of each time slice. I then build an empty list called parts. I loop from 0 up into the total number of partitions, so from 0 to 25. And during each loop, I calculate 3 things: the start of the slice and the end of the slice. I do that by adding the number of seconds to the original start date. Each partition is saved as a dictionary containing the start date time, the end date time, and its index. And then after that, I define the USGS API endpoint, and then I have an empty list called all features, which will store all of the earthquake events. And then I loop over each partitioned time slice one by one. I print out which partition I'm on. I specify the parameters. This parameter includes the start and the end time for each specific slice. And then I get the response. And then from the response, I get the features. And then I append that to this all features master list. Okay, so let me run this cell. So now, as you can see, we're on partition 0, 1, 2, and then we keep going until we've done all the partitions, and then we have all of the data in this all features list. Okay, so in total there were 76,970 events, and that took 28 seconds. And remember, we have to partition. If we don't, this API would have resulted in a 400 error because we've exceeded the number of records per single request. So partitioning isn't optional, but the question is, how do we partition? The problem with this approach is that it's sequential. The reason it's sequential is because it's pure Python code that's running as a single-threaded operation on the driver node. And the reason for that is when you write a regular Python loop, like we've done here, then it processes one chunk, waits for the response, and then processes the next chunk, waits again, and so on. Meanwhile, your cluster, with all of its executor nodes, its CPU cores, and memory, is sitting completely idle. They're not involved at all. All of the work goes through a single core in your driver. The key point that I'm trying to make is that Spark only distributes your work when you use Spark operations, and a Python for loop with requests.get bypasses Spark entirely. So how do we get Spark to distribute our API calls across the cluster? And that's exactly what the PySpark custom data source API gives us. It converts a Python operation into a Spark operation. So instead of one machine making sequential API calls, we have multiple executors making simultaneous API calls. There are 3 classes that we need to implement. Let me walk through each one. We first have this input partition here. This represents one unit of work that can be processed independently. It's just a container for the data that's needed to fetch one chunk, and that is the start time, the end time, and the partition ID for debugging. This object gets serialized and sent to the executors, so it should be lightweight. So let me run this cell. We then have the data source reader. This has 2 key methods with very different execution contexts. This partitions method here runs on the driver. Its job is to create the list of partitioned objects. It essentially plans what work needs to be done. So this will look very familiar to the previous line of code that I ran. So we're essentially just defining a start and end time. We're getting the number of seconds between the start and the end. And then we are defining a step, and then we're creating a partition list. And then instead of a list of start end time, we're getting a time range partition for each chunk. And then we have a list of time range partitions in this parts list. So in the end, we return a list of partitions, which Spark takes and then decides how to distribute across the cluster. This read method runs on the executors. Notice that I'm importing requests directly within the read method, and that is because the code in this read method executes on worker nodes, which may not all have the same imports available as the driver, so you always import inside of read. We then make the API call using the endpoint, and then that partition-specific date range. We do all of our error handling, and then we yield rows one at a time. The fact that we're doing yield is important because we're using a generator pattern, and this is memory efficient because we don't want to load all of the events into memory at once. So let me run this cell so that we've defined this data source reader object. Okay, and then we define the data source object. This is what ties everything together. It's the entry point that Spark calls. This name method is basically the string that you'll use in spark.read.format. So we're using USGS, and that's what we would use. We define the schema for the output data frame. So again, it's the same. It's type, properties, geometry, and ID, where properties and geometry are arrays. And then we define the reader object. This is just an instance of our reader. And then we have the reader method, which just returns an instance of our reader, passing along the schema and the user's options. So let's run this cell. And then this cell just registers the data source so that we can use it. Okay, so now the cell below is using our data source API, which is spark.read.format USGS, and then all of the options, for the same date range and the same number of partitions. So let's see how long this takes, because when we did it using the pure Python operation, it took approximately 28 seconds. Okay, so that took 16 seconds, which is a significant improvement. And the reason it was quicker is because we did it in parallel, and we can actually fine-tune this a bit more so that it's even quicker. So for example, it might run quicker if I reduce the number of partitions. So we can actually just configure this appropriately. But the key point I'm trying to make is that this runs in parallel, whereas the previous Python code, which did a for loop, will not run in parallel. And this also scales linearly with cluster size. So if you add more executors, then you have more parallel API calls, which can mean faster ingestion. Okay, so let's display the data frame. So as you can see, it's exactly the same. So using the Python data source API is not just for API ingestion. You can use it for custom data sources for any source that doesn't have native Spark support. Now I appreciate that this could be a lot to digest, so I'll share links to the Python custom data sources documentation so that you can take a closer look in your own time. Please also go over this Scratch notebook end to end. It can take a while before you're fully comfortable with the code here, because it's not that easy to follow right away. The implementation in this utils datasource.py file is virtually identical to what we just built in the Scratch notebook. So in all of our ETL notebooks, we simply import this module, and then we use it to ingest the earthquake data into the bronze layer. Now that we understand how this USGS data source works, let's walk through the ETL pipeline. I'm going to demonstrate this in the Visual Studio Code Editor, as it's easier to navigate. We have 3 notebooks following the medallion architecture: bronze for raw ingestion, silver for transformation and enrichment, and then gold for analytics-ready aggregations. I'll go through each notebook sequentially, explaining the key sections and the helper functions that we're using. But I encourage you to take a closer look in your own time and go through everything line by line in case anything is unclear. So let's start with this bronze layer notebook. At the top, we have the imports and the widget setup. These widgets become parameters when the notebook runs as a job. You can override them for different environments or date ranges. We then import the various helper functions. We do this from the utils package. The utils package is created from this utils folder, and it's packaged as a wheel when we deploy the project. I'll explain these functions as and when we encounter them. We also have this register USGS data source function. What that does is it creates our PySpark custom data source, as you can see here. So it uses this datasource.py file so that we can leverage our PySpark custom data source to ingest data from the USGS API. And that is what we're doing in the cell below here. We then add some metadata columns via this add metadata columns function. So we add an ingested at and a source column. And then finally, we're writing to the Delta table. This get table path function just gets the table path in terms of its 3-level hierarchy, which is catalog, schema, and table. Once we have that, we use this write delta table with CDF method. This function handles 3 modes: merge for idempotent upserts using the event ID, overwrite for full replacement, and append as well. Change data feed is enabled so that downstream notebooks can read only the changes. So you can see the function here. So that's the bronze notebook. Now let me go over the silver notebook. This is where we transform raw data into a typed, enriched format. The setup is similar. We've got our widgets, and then we're importing all of our relevant helper functions. The key innovation here is that we're relying on incremental processing. So notice this read incremental or full function. Instead of reading the entire bronze table every time, we're using the change data feed from the source to read only the new or the changed records. So this function will check the checkpoint table that we created. If you recall, there's an underscore checkpoint table. It will refer to the last processed version, and it will fetch only the changes from that version. On the first run, it will do a full read, but then subsequent reads will be incremental, and you can see the logic of that here. We then have various transformations. So one notable thing is we're retrieving the event time and the updated time in proper timestamp format, because previously it was in epoch format. And then we're also extracting specific coordinates from the geometry columns. And then we're adding a magnitude category column so that we can classify the earthquakes. We're adding an alert level numeric, a tsunami warning flag, and so on. And then we're adding some data quality, where we filter out records with missing critical fields and we deduplicate by event ID, keeping only the most recently updated version. And then finally, we write to the silver table using the write delta table with CDF function. And we're saving a checkpoint. Once we've processed the bronze table and written it to the silver table, we are adding the latest checkpoint version to that table, so that in subsequent reads, we're reading only changes past that checkpoint version. So we're using this function to do that, which is save checkpoint. So now let me go over the gold notebook. For incremental processing, once again, we're only reading the incremental changes since the data was last processed. We're also identifying affected dates and regions, so we only recompute those aggregations. And that's what this cell is doing. Once we've got the affected dates and the affected regions, we store them in a list. We then create 3 gold tables. Gold event maps contains individual events for the 3D map visualization. Notice we're using the significance column for the severity. Secondly, we have a gold daily summary table. This is aggregated by day for time series charts. And then we also have a regional summary gold table. This is aggregated by region with centroids for mapping. So we contain centroid information here as well, using the latitude and longitude. We write each table using merge, keyed on the date or the region. And then finally, we're once again saving a checkpoint here with the last processed version of the silver table, so the next run knows where we left off. And that's the complete ETL pipeline. To recap, the bronze notebook does the raw ingestion using our custom data source. It stores the full API response as map type columns with CDF enabled. The silver notebook applies typecasting, field extraction, enrichment, deduplication, and it also reads incrementally using change data feed. It also saves version checkpoints on the source table so that it knows where to pick up on the next run. The gold notebook computes pre-aggregated tables for the Streamlit application. You have event level detail for maps, daily aggregations for time series analysis, and regional for the overall summaries. The key patterns we have here are idempotent writes using the delta merge with unique keys, incremental processing using change data feed, and checkpoint tracking, as with the silver layer, so we know exactly where we left off. This means that we can run the pipeline hourly or daily, and it only processes new data. No reprocessing the entire history, and it saves the version checkpoints on the silver table. Now that we've gone through the ETL logic, let's finally go over the Streamlit application. The code for the application is in this Streamlit_app folder. A Databricks app needs 2 files, app.py and app.yaml. I have them both open here. App.yaml is our configuration file. Think of it as the settings for the application. It tells the system how to run the app via this command key. So it should run streamlit run app.py. And then we have environment variables consisting of the warehouse ID, the catalog, and the schema. App.py is the actual application. All of our Python code lives here. The UI, the database queries, the map, the charts, everything. So we're importing all of the relevant modules, we're setting page configurations, and then we're also importing the environment variables. Notice this SQL query function. It connects to our Databricks warehouse, it runs queries, and then it spits back a pandas data frame. Notice how it's grabbing the warehouse ID from the environment. We're then querying and loading our gold tables using this load events function, load daily summary function, and load regional summary function. We're caching the data for 5 minutes. And this is for efficiency. We then have remaining lines of code. This is to set up the application assets, such as the sidebar, the charts, and the tables. I'm not going to go line by line here. If you know Seaborn or Matplotlib, Streamlit will feel very familiar. It's just a different visualization library, and it's really easy to pick up if you just refer to the official documentation. But let me pick out one thing. If I scroll further down, you can see that for the 3D map, I'm using PyDeck, hence pdk.layer. So I'm using PyDeck's column layer. Column height and color are both driven by the significance score. As you can see, elevation is just the significance. That will determine the height of the bar. We also get the positions by the latitude and the longitude columns. The rest is just standard Streamlit. Deployment is automatic with the bundle. So when you run Databricks bundle deploy, it will automatically deploy this application. And it does this because of the configuration in this databricks.yaml file. So as you can see, we've specified the source code for the Streamlit application. So that's just a quick summary of the Streamlit application code. For more on Streamlit, PyDeck, and Databricks apps in general, I'll link some official documentation. The patterns that you use are standard, so any Streamlit tutorial will help you extend this dashboard. Okay, so that's the end of the walkthrough. I demonstrated how you can build a fully deployed, production-ready earthquake analytics platform running on the Databricks Free Edition. If you've made it this far, then genuinely well done. I intentionally made the project challenging. I didn't want to create a tutorial where everything works perfectly without any adjustments and just fits into neat little boxes. Real-world data engineering isn't like that. You need to think about system design, incremental processing, packaging and deployment, and so on. My hope is that you picked up a few things along the way and became a slightly better data engineer. If you found this end-to-end project valuable, then please do like and subscribe and share the channel with anyone you think would benefit. It really does help me grow my platform. I'll leave links to my LinkedIn, my online courses, and the GitHub repository in the video description. Thanks for watching, and I'll see you in the next one.